This episode was brought to you by the Music for Scientists album, now available on all streaming services. You can check out the music video for the song The Idea at the link in the description. Here at Journey to the Microcosmos, we have a small team of people working to make these videos for you every week. First, there's me. Hi, I'm Hank Green, your narrator. And then there's James Weiss, our master of microscopes, providing all of the beautiful footage you see on your screen. Matthew Gatos is our producer and editor, taking my narration and James's footage and turning them into actual videos that you can watch. And last, but certainly not least, is Deboki Chakravarti, our writer on Journey to the Microcosmos, the person who brings the microcosmos to life with her storytelling and her exhaustive research. Deboki has been with the channel since almost the very beginning. In fact, the first script she ever wrote for Journey to the Microcosmos was our episode about diatoms back in 2019. And since we're here today to discuss diatoms once again, we thought it would be fitting to use this opportunity to introduce Deboki's new role as another host of Journey to the Microcosmos. I'll still be here narrating most of the episodes, but from time to time, you'll hear Deboki hosting a video instead of me, with her experience not only in writing over 70 episodes of Journey to the Microcosmos, but also with her PhD in biomedical engineering and as a host on Crash Course Organic Chemistry. I could not be more excited to have her join me on this journey. So now, I'm going to hand the microphone over to Deboki so she can teach you more about diatoms.
Wherever you are on your journey to the microcosmos, the odds are high that you'll run into a diatom. They're both abundant and easy to spot because of the shells they encase themselves in. The results are beautiful, exacting geometries that create a living kaleidoscope in the microcosmos. And even if you lived your entire life without ever seeing a diatom, without ever hearing the word diatom, you would still be living a life that's shaped by them, all the way down to the oxygen you breathe, thanks in no small part to their outsized contribution to the world's photosynthesis. But what remains captivating about diatoms is, well, the thing that remains, even when the diatom itself is gone. The hard silica shell they once lived in, also known as the frustule. We've talked about frustules a bit before and how they've given diatoms the nickname jewels of the sea. And today, we're going to dive a bit more into how those frustules are made and the role they play in our world. Diatoms are the architects of their own glass houses, and the scale of this project is immense. These silica shells aren't just a smooth, uniform exterior. There are pores and elongated channels creating ornate, microscopic patterns that the organism depends on to survive. The source of the diatom's building blocks is geology. As rocks and land get weathered and eroded, silica enters the water, where it dissolves into silicic acid, which can then diffuse into the diatom and get converted into silica. But if diffusion isn't bringing in enough material, the diatoms can also rely on silicon transporter proteins in their membranes to gather more. Inside the diatom is a special area called the silica deposition vesicle, and it's there that the silica bits get linked together to form bigger and bigger pieces. But while we know that this is where the silica walls get put together, the chemistry and biology of how they get put together is still unclear. We know that the silica can itself form a gel-like network, so that could make up a key assembly step. But there may also be other organic molecules, like proteins, that bind to the silica and help create the final structure. While scientists are still untangling those mechanisms, they have observed the way that the silica deposition vesicle and other structures in the cell, including the mitochondria, can help to mold the shape of the final silica structure. For example, elongated symmetric diatoms, also called pennate diatoms, often have a slit called the raphe. The slit helps the diatom move around, serving as an opening through which they can secrete a viscous fluid to glide on. And one of the ways that diatoms make the raphe is by physically molding it through the arrangement of their microtubules. Many diatoms are non-modal, meaning they don't move around. And the lack of visible movement from the outside is striking when you consider all of the activity that has gone on inside of them to make those frustules happen. Like we said earlier, they're doing more than creating a smooth, transparent surface. They're creating a molded, ornate structure, personalized to their own shape, like a house couture. And not only is this process a lot of work, it renders diatoms dependent on silica, a chemical they can't make for themselves. So why do it? Well, for one, it's cheaper than both making and assembling your own materials. The silica is already out there, so why not take advantage of it? One study found that the materials in the diatom's frustules might help the organism take in carbon dioxide, improving their photosynthetic capabilities. These advantages seem to translate over into the immense capacity of diatoms to grow and dominate over other algae that share their waters. But taking over a body of water is all fun and games until the silica runs out. Diatoms are known for their ability to form large visible blooms, whether in your local lake or the Arctic Ocean. But scientists studying those Arctic blooms found that as the diatom population expanded, they also depleted their waters of silicic acid. And that in turn halted their growth and began to increase the number of dead diatoms. And both of these things, the lack of growth and the dying, have another impact on diatom populations: sinking. Healthy growing diatoms can up their buoyancy to keep them afloat, while dying cells cannot. It might be sad to imagine those blooms dying and descending to lower depths, the ornate jewels collapsing like a microbial empire. But nature doesn't trade in inconsequential tragedies. The death of diatoms leaves behind frustules like this one, which means it leaves behind silica. Some of that silica can be recycled by other diatoms, but over time it will eventually descend further and further down until it gathers on sediments. When a diatom takes in silicic acid, it's taking in the remnants of a geological process, the weathering and erosion that brought the silicon to water in the first place. And then through the construction of its shell, it recycles and transforms the dissolved silicon into a form that can become geological once again. And how that silica gets used again can vary, but as always with the diatom, your chances of running into it again are high. Scientists found that dust from a diatom shell-rich sediment in Chad might travel as far as the Amazon. The diatom itself may not be making the trip, but the microcosmos and the things built in it have a way of sticking around. Thank you for coming on this journey with us as we explore the unseen world that surrounds us. This episode is brought to you by the Music for Scientists album, which was created by composer and musician Patrick Olson. The album is inspired by the intersection of science and art. And if you're looking to explore that intersection more, check out the music video for one of the tracks on the album called The Idea. The music video for this track was produced from a sequence of 15,000 photographs of 3 traditional paintings by artist John Todd. His painting style was then transferred to a video performance by using a form of machine learning, and the song itself is all about exploring how we form ideas. If you think this sounds like something you might enjoy, click the link in the description to see the video or stream the music on all major music services. The names on the screen right now, those are our Patreon patrons. Without them, we could not make this show, and we are so thankful to them. If you like what we do and want to help us keep making it, you can join those people at patreon.com/journeytomicro. If you want to see more from our master of microscopes, James Weiss, check out Jam and Germs on Instagram. And if you want to see more from us, there's always a subscribe button somewhere nearby.